talked about basically lines, or we start with points, then we went to lines and rays and angles, then we went to triangles. Okay, now we are going to quadrilaterals. Okay, so we've done this. This is basically a three-sided figure. A quadrilateral is a four-sided figure. It has four sides. Okay. This is 7-1. We're doing quadrilaterals. Okay. There's two different kinds of quadrilaterals. Okay. And this is true in all types of figures that have lines in them. There's called what's oops, I can't write that. Convex, which is what we normally think of quadrilaterals as being. What that means is how, if I draw the quadrilateral, if I put, anywhere I put 2 points, it will stay inside. It won't go out or cross the lines, okay? So if I pick 2 points anywhere in the quadrilateral, that line will be within, okay? So that's convex. Concave is when we have something like that, it caves in on itself. That's how I say you notice it, because it kind of caves in. It looks like a cave there. But notice if I put 2 points over here, I go outside the quadrilateral. I go outside of it. So this is concave when you go outside. This is convex when you always stay inside. And I basically look, does it cave in? It looks like it caved in on itself, okay? And so that's how I look to see if it is, good morning, if it is convex or concave. We are gonna deal mostly with convex quadrilaterals is what we're gonna talk about. This is just so you know it. The things we talk about don't always apply to all quadrilaterals. It might just apply to specific quadrilaterals that are convex. Okay. So, that's the first thing. Okay, in a quadrilateral, that is convex. Does anybody know what the sum of the angles equals? Yes.
180.
Nope, that's a triangle. If I take a triangle, all of those add up to 180. Yes.
360.
360. Think of a square. A square is the most basic quadrilateral you can have. Okay? And it is 4 right angles. So the angles equal 360 degrees, okay? So that's something we can say about all of those, all quadrilaterals, is that you're gonna always get 360. And again, to remember it, just draw your basic, well, that's not very good, but a basic square. 4 times 90 is 360. So if you don't remember, just draw the basic square or rectangle and you will know what it always adds up to be. All of them add up to that as long as they're convex. Okay? The other ones do not add up to 360 degrees. Because you've got that concave part in there. So those are some things that we can have. That's lousy. Much better. Okay, what are some types of convex quadrilaterals that you guys can think of? We have quite a few, actually. So what are some of them? Types of quadrilateral.
Rectangle.
Yes, one is a rectangle.
Do diamonds count?
Do what?
Does a diamond count?
A diamond counts, yes.
Square.
It's actually a square.
Just rotate.
Yeah, it's rotated. So I'm gonna put that up here,
It
a
has
square or a diamond, if you wanna call it that.
Longer sides.
Okay?
Isn't there one called a parallelogram?
There is one called the parallelogram. I call it the slanted square or slanted rectangle, but it doesn't have 90 degrees. So these all have 90 degrees for all four angles. These have sides, all sides are equal, like an equilateral triangle, a square is. Up here, opposite sides are equal. And then the parallelogram, which I like to call the slanted rectangle. Okay, the degrees are not necessarily 90 degrees, okay, but opposite angles are the same. Opposite angles are the same. So in this one, opposite angles are equal and opposite sides, opposite angles and sides are equal. Obviously, the opposite sides are parallel also. But that's true up here also. Okay. So that it's named a parallelogram because the opposite sides are parallel, but really it's the opposite angles and sides are equal is much more useful to us than the other. Okay. Can we think of another kind that we have? Let me see if I even have. Oh, I guess it just, yeah, it does, kind of. No. Well, there are just four-sided ones.
Three-sided quadrilateral.
Nope, there can't be a three-sided quadrilateral. Okay.
It's like
We
the
do have
definition in the
one that's called a kite. Okay, a kite is basically where so it looks like this. So I'm not sure how to say that, but it's the two top ones are the same and the two bottom ones are the same, like that. Okay. Opposite angles not necessarily equal. Okay. These angles are definitely equal. Okay. So in this, it's the, let's see, two coinciding sides are equal. And these angles over here, the angles between the two, the angles between the two pairs of equal sides are equal. That's harder to say to me than just drawing that picture. That picture tells me a lot more. These sides are equal, these sides are equal, and these angles are equal. We can't necessarily say anything about that. Okay, so that's one of the things you can say. So those are the types of rectangles or quadrilaterals that we normally talk about. They're specified, but you can have unspecified quadrilaterals also, which are just four sides that don't necessarily, well, I guess there's a trapezoid. Forgot trapezoid. Trapezoid is the other one that we normally talk about. And a trapezoid has one set of parallel sides. So it looks basically like this. Actually, I'm gonna do it like this. So it doesn't matter as long as one pair are parallel, then that's a trapezoid. So it does not have any congruence on everything else. The congruency is not there because the other lines don't have to be parallel to each other. So the last two, the three at the top are pretty easy. We see those all the time. A kite we do see sometimes because we know what a kite shape is. And then the trapezoid is probably the one we don't talk about a lot. And I'm not even sure where it came up with the word trapezoid. I should look that up sometime and see. Kind of interesting sometimes on these. So, okay, so right now we're going to look at just some of the basic ones. Okay. First thing is defining what a diagonal is. A diagonal is when you take 2 points that are not connected, okay, two, what do we call those, vertices that are not connected and connect them, okay? So it's non-adjacent, so you connect, it's the line, I should say, the line connecting two vertices that are non-adjacent. Okay, so in any, you can draw any, the diagonal goes up from there to there and down to there. So those are diagonals of your quadrilateral. So it's just taking the two opposites, two non-adjacent ones and connecting them. So these are two diagonals. One, this, two, here. Okay, so those are called the diagonals. So we'll be referring to diagonals when we're looking at this. Okay, so we're going to be talking about diagonals. Again, a lot of geometry is definitions and knowing what kind of things are true about those. Okay, and that's really what we're doing in geometry, and that's why we do a lot of proofs to prove something's true based on all those definitions and all those things. But again, like I said, we don't use this in real life. You're never going to prove something like that. We use those things in real life, especially about rectangles and all that kind of stuff. If we're squaring up when we're building things, you do that a lot. Okay. But also getting used to, that's why I had to do the history project, getting you used to using arguments, okay? And looking at the assumptions, then giving reasons why, based on some of those facts that we assume. Okay, so that's diagonals. Basically, yeah, it's equiangular. If it's a rectangle, don't need to tell you that. Okay, so that's pretty much section 7.1 and a little additional stuff that I added in because they don't really cover all this in section 1, but I just thought I'd throw those things in there. Okay, So we're gonna go into section 2. Section 1 just talks a little bit about a rectangle, but it says if all of the angles are equal, you have at least a rectangle, which should make sense. If they're equal angular, you do have, these are really terrible erasers. I'm even using an expo marker, okay. So if you have all equal angular, all the angles are equal in a quadrilateral, then you know it's a rectangle or a square, okay? Rectangle is the most basic one that you do because we know that for sure. We don't know it's a square unless we know all the sides are the same, okay? So the next one is parallelograms. So 7.2 is all about parallelograms. Okay, and parallelograms, I call it the slanted. Oh, by the way, a rectangle is a parallelogram because it does have both sides that are parallel to each other. So a parallelogram, a rectangle fits as a parallelogram. So a rectangle is a parallelogram. But we don't usually refer to it as a parallelogram because rectangle is more specific. Because it has all 90-degree angles, it's equal angular, where a normal, any other parallelogram is not. Okay. So we already know that opposite sides are the same. We know that. Opposite angles are the same. So that's what's true in a parallelogram. We know that they are all the same. Okay, some other things that we know about them is if I have a parallelogram like this, if I put their diagonals in, that's not accurate, but okay, they bisect each other. So the diagonals of that's my short for parallelogram to things like that that are next to each other, are bisect each other. So this is what we know is true. That also is true if we look up here. If I can't draw this, but if I draw in a rectangle, those are not diagonals. What am I doing? If I draw the diagonals here, they all are the same there because the diagonals are the same length. So they're all the same, but the diagonals always bisect each other when you have a parallelogram. Okay. Okay, the last thing is we're going to talk about symmetry. Okay, so we have already talked about line symmetry. Okay, line symmetry is something we've already looked at, and it's when I take something like our kite, it has line symmetry, and I can cut it down a line and fold it across that line, and it will be equal on the other side. That's line symmetry. Okay, so another example of that is if I have I'm a terrible drawer. If somebody can draw an actual really good heart, it has a line symmetry. That one does not, but if you can draw it really well, that has line symmetry because I can fold it in half and it will be equal on both sides. Okay, so line symmetry is always folding it across a line. We're gonna talk about a new symmetry today. It's called point symmetry, okay? Point symmetry is different. What it is if you can find a point in the figure and you can rotate 180 degrees, it will match. Okay, that's kind of hard. So I'm going to show you, because I wanted to show everybody something like this. Okay. That one does not work. That one does. I think these do. Let me see. Oh, yes. Okay. I think all of these do. Okay, so there's an ace, a 9, and a face card. Okay, so look at the center and see how you can rotate those around. So if you take, it will give you the same thing. Okay. Okay, here's a face card. I want you guys all to look at all of them. Here's a 9 and a king. And I'm gonna go ahead and give you guys a 5 also, just so you can, since there's 2 of you there, there's 4 of you. Yes, yeah. On these, but I just want you to see how that works with these cards, okay? So, notice with these,
Yeah, you can even do it with the
points
back.
in the center,
That's
and
upsetting.
rotate this
Wow,
finger,
it's
will
not-
match up with
It's not.
this. Same thing here, if I
That's-
pick in center,
What?
It
rotate
actually-
this. Well, actually, they won't
Yeah,
rotate,
yeah.
they won't match.
The spades.
That one does not work. An ace does not work. Did I give you guys an ace?
These don't work. These
Yeah.
are
Which
always
ones?
different. They're not symmetric.
Because they're not.
Wait, what?
You're right.
If it's in.
Diamonds do.
Yeah.
Wait, just look at the back side. Back side.
Here, that diamond does.
The face cards.
Right.
Wait, don't you just have to have an even number though?
I gave you the wrong one.
No.
It's this one.
Yeah, this is.
How is that not?
Yeah.
What?
What was the third card you had?
You took my.
Oh, you're right. Yeah, that's true.
Diamonds do work.
Diamonds work, yeah.
Hearts do not.
Hearts don't. Pretty
Clubs
much only
don't.
diamonds.
Only diamonds. Here's an example of one.
Let's see if this will work.
So do you see that? So let's now look at the ones that don't. So compare to ones that don't.
It's not, it's not like I'm taking her.
Anyway, so look at those and see why they don't work.
The blizzard.
Okay, compare these to the ones that don't work.
That's like very good. Because if you,
This one.
dude, I bet you that's bad.
The thing with.
Yeah, but there's one that's almost right.
Contemplate.
This does not work either. See,
Yes,
Wow.
there is.
Quite fascinating.
Yep.
Yeah, just, I wanna know.
Oh wait, like.
Farmhouse.
Wait, but no, there's a line of symmetry, but there's no points.
Dude, they're so impossible.
Actually,
You like put
there is,
chalk.
this is not a line of symmetry,
Oh.
cause the tens are in opposite corners.
Yeah, now we know.
Well, I'm talking about this one.
Still not, because see, the eights are in different
Oh.
corners,
Okay.
okay? So the question is, do these have points of symmetry?
No. Oh wait,
Do
But
these
that
have points of
yes.
symmetry?
Yeah.
Yeah.
Yes.
No.
Yes.
No.
Because they're
100%.
pointing the same way. Or they're all pointing. They're even.
Dude, you can cut it straight down the middle.
No, if I cut it down the middle, that's a
other way.
line of symmetry,
She's
it's
asking
got-
about it.
okay?
it's got-
And it's not the same because the tens are not across from each other, so there is no line of symmetry.
Let's talk the other
There's a
way.
point of symmetry.
This way, again, the tens are not in the right place. To be a line of symmetry, that 10 has to be there. Okay. Could I take a point right here and rotate this so it's the same?
Ooh, I think on that one you technically can because it's 5 and 5.
Yes,
See how we
because
get it.
when I rotate it now, these will flip upside down. You cannot do it if there's a, this is a, what kind is this? It's not a spade, it's a club.
Yeah, that's
Okay, the clubs do not work if you have one in the middle because they are not, you can't reflect it and get that other one, okay? This one also works. Okay, the 10s work also. So I might have you later give out parts of different cards to you and have you guys go through and figure out which ones do rotate and which ones have, if any, have line symmetry.
No, we did have line symmetry.
Anyway, I thought point symmetry would be easier to show this way. I have a hard time drawing line symmetry or point symmetry. The one thing that we do know is that parallelograms, a true parallelogram, if I drew it right, has a point of symmetry that we can rotate it to get, so it has a point of symmetry. It actually does not have line symmetry. Why? If I folded that in half, would they be equal? No, because if I folded it right down here, what's gonna happen is this one is longer and it's not gonna match up with that one, okay? So depending on how long I draw it, okay? But it does have point symmetry. This is no line, but if you look at it, I try to draw it more like this. It does have a point symmetry because I can rotate it and it will fit. Okay, so it does have point symmetry. So that's the difference on those. Okay. So that's really all of section 7.1 and 7.2 that we've just gone through. Okay, so those are the two things, the two extras, or the two sections for today. Okay, so